In the dry ice puck lab, you had a puck traveling down a frictionless ramp, and 0 was at the top of the ramp, and the positive direction was down the ramp. You made a position versus time graph. It looks something like, I wonder if we can do this. Something like this. Position was in centimeters. Time was in this weird unit that we call the click. And for most of you, 30 clicks is about the maximum value for ramp number 8. And that got us to about 150 centimeters down the ramp. And we said things like, this puck started at position 0 and traveled in a positive direction, and it sped up as it traveled. And we talked about how we could tell that it sped up because if you picked equal increments of time, oh, that was pretty good. If you picked equal increments of time, then the position changed by a greater and greater amount for every equal increment. So for the first 5 clicks, the position increases a little bit, but for the next 5 clicks a little bit more, and the next 5 clicks a little bit more. So now that I've put some numbers on this graph, what I want you to do is see if you can tell me, over the 30 click time interval from beginning to end for this puck, what was the average velocity? Hopefully, you guys remember that average velocity is defined as the slope of a position time graph. And this is kind of weird because that slope keeps changing, but you can kind of imagine average velocity this way. If you look at the first clock reading in your time interval and the last clock reading in your time interval, and you just draw, let's see if you can just draw a line that connects those 2 points, something like that. If you find the slope of that connecting line, you're finding the average velocity. So if I find the slope of that connecting line, I can use my positions at those 2 points. So that's going to be average velocity is going to be 150 clicks. No, 150 centimeters divided by 30 clicks. Or 5 centimeters per click. And remember what that means is that for every click of time, the position of the puck changes by 5 centimeters. Now that's kind of weird because, does it? So most of you probably understand that this 5 centimeters per click is an average. It means over the whole 30 clicks, you can imagine that the puck changes position by 5 centimeters every click. But you know, early on maybe not so much, and later on not so much, and in the middle not so much. So let's think about how can we find the velocity, not an average velocity, but an instantaneous velocity. How fast is it going right now? Or kind of like when you take a trip in a car, you can say, oh, you know what, I'm driving up to Chicago this weekend and it's going to take me 5 hours to go about 300 miles, so I'm going to average about 60 miles per hour. But if I want to know how fast I'm going right now in my car, I need to look at the little speedometer. So if we could stick a speedometer on this puck and see how fast it's going right now, how would I go about finding that instantaneous velocity from this position versus time graph? I'm going to start by thinking that, let's say we have 2 students, student A and student B. Student A says that at time 20, the instantaneous velocity is greater than 5 centimeters per click. But student B says, nah, at time 20, the instantaneous velocity is less than 5 centimeters per click. Which student is correct, and how do you know? You might reason through this by saying, well, from time 0 to time 30 is a big time interval, and it's too big to say how fast am I going at 20. So what if we scooch the first point up a little bit and said, hey, let's look at time 15 to time 30. Then you can imagine that a connecting line might look something like this. And the slope of that connecting line tells me what? Yeah, the slope of that connecting line tells me the average velocity from time 15 clicks to time 30 clicks. And you can already kind of see with your eyeballs that the slope of that line is bigger than the slope of the line from time 0 to time 30. So my average velocity for the second half of this trip is bigger than the average velocity for the whole trip. But is there a way that we could find the instantaneous velocity at time 20? What if we scrunched our points even a little closer? Something like maybe that. Then we could draw a connecting line that might look something like this. Only better. Right? Or what if we got them really close and picked two clock readings that were like right almost on top of that 20-second. Okay? Then we could draw a connecting line to find the average velocity for that tiny little time interval. So I think you can kind of see where this is going, is that if we bring those points closer and closer and closer together, we're not really looking at the slope of a connecting line at all. Instead, we're looking at the slope of a line that touches that curve just at that one point. I wonder if I can actually even draw this right. So that is now a line. It's not called a connecting line anymore. That's called a tangent line. And a tangent line is a line that touches a curve at just one point. And the cool thing is that for any given curve, or for any given point on a curve, there is only one tangent line, one correct tangent line. So we're kind of eyeballing it here, but hopefully we'll get close to the one actual tangent line. Anyway, the neat thing is, if you find the slope of that tangent line, you are finding the instantaneous velocity. So if I draw a tangent line to the curve at t equals 20 clicks, if I find the slope of that line, it's going to be the instantaneous velocity at t equals 20 clicks. And you can see that the slope of that line is going to be bigger than the slope of the connecting line from time 0 to time 30. So let's say we've got this position time graph, and what I want you to do is redraw your angle 8 data onto that special graph paper, because that will make a nice big graph that should use almost the entire sheet of paper. And if you wanted to make a velocity versus time graph from this graph or from this data, how would you do it? If you want to make a velocity versus time graph, what you're going to need to do is find a whole lot of instantaneous velocities at different clock readings from this graph. And to do that, you're going to need to draw a whole bunch of tangent lines. So on this graph that you've redrawn, you're going to get yourself a ruler and a bunch of colored pencils, because this will be easier to do if the lines aren't all the same color. But once you've got your smooth curve drawn on this graph, you're going to take your ruler and you're going to start drawing tangent lines. So, let's see. At t equals 3, maybe the tangent line looks something like this. That's not bad. Okay. And I want you to make it look just like this, where you go all the way from the x-axis all the way out to the right edge of the paper. Okay, and the reason for that is, if you now find the slope of this graph, the slope of this tangent line, if you pick points that are far, far apart, that'll probably give you the most accurate answer for your slope. But the slope of that tangent line is the velocity at a clock reading of 3 clicks. Then you're going to grab a different colored pencil, And you're going to draw a tangent line from a tangent line at t equals 6. So that might look something like this. Okay. And again, you're going to go through and you're going to figure out what the slope of the tangent line is, and that slope is the instantaneous velocity at t equals 6. And then you're going to grab a different color. You're going to do that at t equals 9. Wow, that was a terrible t equals 9, sorry. Now we have to go through this weirdness of trying to fix my picture. Oh, that wasn't bad at all. Oh, the snap is killing me. There we go. Okay, so there's my tangent line at t equals 9, and I do t equals 12 and 15 and 18 and 21 and so on until we get to whatever your maximum number that you can get to that's a multiple of 3. Is that making sense? I hope so. So you're going to have your tangent lines drawn all over your graph, and then you're going to calculate your slopes. Because the slope is the instantaneous velocity, right? So you could just say something like, hey, k is change in position over change in time, even though it's not really, right? This is kind of an imaginary change in position, change in time, but whatever. Pick 2 points on your tangent line, calculate your slope, general equation, plug in some numbers, blah, 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 k equals something. And now, so you do that for each one of your tangent lines, and then make yourself a data table. Instantaneous velocity. Notice that there is no bar there because the bar is average velocity. At time 0, the velocity is 0. 3, 6, 9, 12, 15. And then you just fill in your slopes here. And then finally, you make me a graph of the instantaneous velocity versus the clock reading and plot your points. And then hopefully you can do some kind of mathematical analysis, or maybe you'll have to read your fat packet to do that. But that's your assignment for the weekend.